Welcome to this lecture series on semiconductor physics, where I will be guiding you through this entire chapter. It is a rather more theoretical chapter, so we will be going through it step by step. So, the first thing is that let's talk about bonding forces and energy bands in solids. So, in solids, electrons are restricted to sets of discrete energy levels within atoms with large gaps among them where no energy state is available for the electron to occupy. So basically there are discrete energy levels where electrons occur, and there is no intermediate state within these discrete levels where the electrons can stay. So they are bound to these fixed energy levels. However, what happens in a solid is that these wave functions start to overlap, and as a result, from the neighboring atoms, the electrons, their wave functions basically start to overlap, and it affects the potential energy and the boundary conditions in the Schrodinger equation, and different energy levels are obtained. Also to be noted is that an electron is not necessarily localized in a particular atom inside a solid. Now these can be treated as a small contribution, giving rise to shifting and splitting of energy states into energy bands. So we already know about different types of bonding. So ionic bonding and metallic bonding, covalent bonding and mixed bonding. Let's skip the bonding part because it's very easy and can be considered as a prerequisite for this course, and move forward to energy bands. Now when isolated atoms are brought together to form a solid, the electron wave functions basically start to overlap. Now after this wave functions initially start to overlap, they find their peace and they settle down at a proper interatomic spacing where the attraction and repulsion forces basically are balanced. And due to this reason, basically what happens is that the initial discrete energy bands, they start to split, and then multiple energy bands are found out. Now we know due to Pauli's exclusion principle that these bands, they need to split belonging to the pair of individual atoms, and in a solid, due to the large number of atoms, these energy levels basically appear continuous, and we can treat them essentially as a band. So if you look at this diagram, so here we have a carbon atom. Actually we see the bonding of carbon atoms to form a solid. So we have 2s, 2p. 2s has 2 n states and 2p has 6 n states. This should be pretty self-explanatory. And then what happens is that as the atoms come closer together, the interatomic distance decreases and their energy levels, so both 2s and 2p, they start to split until a point appears at which the energy levels have merged, and in this merged place we cannot separate the initial discrete stages. After that, the interatomic forces find a balance and we develop this energy gap where there are no states. However, we find two well-defined states getting separated with an equal number of states. So 4n states and 4n states. However, these two bands are completely separate and they have a very specific band gap between them, which we will talk about soon. This is how we can treat atoms coming closer and falling into specific interatomic arrangement to form a solid. Similar diagrams can be obtained for silicon as well. Now, imagine formation of a diamond crystal from isolated carbon atoms. So each atom has two 1s states, two 2s states, 6 2p states and higher states. For n atoms, the number of states are 2n, 2n and 6n of types 1s, 2s and 2p. So basically we are talking about the structure of a carbon atom here. Now with reduction in interatomic spaces, these energy levels split into bands, and the 2s and 2p bands merge into a single band having 8n available states. So basically this middle portion where the 2s and 2n states have merged and all the 8n states are there in this single band. You cannot differentiate between the 2s and 2p states at this point. Now as the interatomic spaces approaches the equilibrium spacing of diamond crystals, this band splits into two bands having an energy gap Eg where no allowed states for electrons exist. This is known as the forbidden energy gap, and we will understand why this is very important. Now, the upper band is called the conduction band, which actually allows electricity to flow through, and the lower band is called the valence band, which is tied to the valence atoms in the semiconductor. Now, the lower, I use this term semiconductor very loosely here, but we will learn very intricately what semiconductor is very soon. Now, the lower valence state is filled with 2n electrons. However, the 4n electrons residing in the original n is equal to 2 state will now occupy states either in the valence band or in the conduction band. So, the 2n states basically, so the 1s band with the 2n electrons, they remain untouched. The 1s band we have not shown in the diagram, but even if it was shown in the diagram, we would see that it is a constant state because bonding does not affect the one shell. However, the 2 shell actually does go through bonding, and as a result, those states, those electrons residing in n is equal to 2 will now occupy either the valence band or the conduction band depending on where they exist. Now at 0 Kelvin, the electrons will occupy the lowest energy states available to them. Thus, the 4n states in the valence band will be completely filled, while the 4n states in the conduction band will be completely empty. Now, we will come to the significance of 0 Kelvin a bit later, but keep this in mind that regardless of the material, at 0 Kelvin, most electrons will try and occupy the lowest possible energy level, which in this case we have learned is the valence band, and the higher energy level conduction band for carbon, which we are dealing with here, will remain empty. Now, it is not because that it is because of the fact that the electrons are preferring the lower energy state. However, if you had more electrons and lesser number of states in the valence band, then those electrons would have to occupy the conduction band by default. Now, for electrons to move under an applied electric field, there must be states available to them. A completely filled band cannot contribute to transport, neither can a completely empty band. So at 0 Kelvin, these semiconductors which we have talked about are perfect insulators. Because all of the electrons are in the valence band, basically the conduction band is 0. Now with thermal or optical excitation, some of these electrons will be excited, and this allows the conduction of electricity through these semiconductors. Now at temperatures other than 0 Kelvin, the magnitude of band gap separates an insulator from a semiconductor. So basically, the gap which we discussed, so this gap, which is denoted by Eg, this decides whether our semiconductor will be conducting electricity or not. So if you see, let's say diamond has 5 electron volt, silicon has 1.12 electron volt. This is the required energy for the semiconductors, or the required potential for the semiconductors to start conducting electricity. So with a higher band gap, suppose diamond has 5 electron volt, so we say that diamond is an insulator. It does not mean that diamond cannot conduct electricity at all. It means that we need to give relatively a very high voltage for it to conduct electricity. And the same thing applies for silicon as well. Now, for silicon, you see that Eg is actually low. So 1.12 electron volt is much lower. So silicon we can treat as a semiconductor. But also we want a sufficient amount of Eg. So if we take, let's say, some metal, then this Eg would be very low. Then we can just simply treat it as a conductor because it will start conducting at very low voltages. The number of electrons available for conduction can be increased greatly in semiconductors by a reasonable amount of thermal or optical energy. In metals, the bands are either partially filled and they overlap. Thus, electrons and empty states coexist. This results in greater electrical conductivity. Basically, the bands are either partially filled or they perfectly overlap. Basically, I need to explain this a little bit. That in a metal, what happens is that the energy levels, so the conduction band energy level and the valence band energy level, they can overlap, and as a result, the electrons and the absence of electrons, they can coexist together. And what can also happen is that they are both partially filled, which either of the two scenarios results in much greater electrical conductivity. Now, direct and indirect semiconductors. So, in a typical quantitative calculation of band structures, the wave function of a single electron traveling through a perfectly periodic lattice is assumed to be in form of a plane wave moving in the x direction with a propagation constant k, also called a wave vector. In quantum mechanics, the momentum can be given by P is equal to h bar k. So basically this is the equation for momentum of an electron moving through a solid. So it is the wave function of a single electron moving through a perfectly periodic lattice. So the space dependent wave function can be given like this, and we will come to why it is important, where u kxx modulates the wave function according to the periodicity of the lattice. Allowed values of energy, while plotted as a function of k, gives the ek diagram. Since the periodicity of most lattices is different in various directions, the ek diagram is a complex surface which is to be visualized in 3 dimensions. So direct and indirect transition of electrons from conduction band to the valence band. Now this is actually a very important diagram to see and analyze. Take a look at what is happening. We have got this formula for the momentum of an electron, and we have got this equation for the wave function. Now, by plotting the allowed values of energy as a function of k, which is this, so basically directly proportional to the momentum of an electron. So basically we are plotting the proportionality constant of the momentum of an electron with respect to the allowed energy states. We get this kind of a diagram. So if you look at these diagrams, you will see something very complex actually happening. However, if you analyze it, it is actually very easy. See, these two represent two types of semiconductors. This is a direct semiconductor and this is an indirect semiconductor. Now, if you look carefully, in the direct semiconductor, at, let's say this be the valence energy level and this represent the conduction energy level, we see that an electron simply has to jump through this Eg band gap, and if electrons transition from the conduction or valence band, so here it is shown that it is transitioning from the conduction to valence band, so it is actually giving away energy, so it should give away some form of light or radiation, which we can calculate by h nu is equal to Eg, because Eg is the band gap which is being jumped by the electron. However, in case of indirect semiconductors, the condition is not so simple. The conduction band is shifted in terms of k. As a result, this electron will actually not only be at a higher energy level but at a higher momentum than the electron over here. So initially we only had an energy difference. Now we also have to take into consideration a momentum difference. As a result, the electron initially has to slow down its momentum and then decrease its energy level to go into the valence shell. As a result, this gap, which we initially called Eg, makes no sense over here because the momentum has also been shifted. Now, why this happens, we will learn here. So, direct band gap semiconductors, the minimum of the conduction band and the maxima of the valence band occur at the same value of k of an electron, making the smallest energy transition from the conduction band to the valence band, and can do so without a change in k. Basically, they are trying to say is that the minimum of the conduction band, so we are basically talking about this point, and the maximum of a valence band, so we are talking about this point, right? So these occur at the same value of k for an electron, so the momentum remains constant throughout these points, and as a result the electron can transition without a change in its momentum. Now, indirect band gap semiconductor, the minimum of the conduction band and the maximum of the valence band occur for different values of K. Thus, the smallest energy transition for an electron requires a change in momentum. So even the lowest transition, so the smallest energy transition here is of course the shortest distance between the two curves. Here it has to first reduce its momentum and then go through here. Once again, the shortest distance is the maximum of the valence band and the minimum of the conduction band. Now, why we are taking into consideration this maxima and minima is another story which we won't get into. It is beyond the scope of what we are learning. Now, electrons falling from conduction band to an empty state in the valence band, this is known as recombination. So, an electron which jumps from the upper curve, so from this curve and goes to this curve, in both the curves, this process is known as recombination. Recombination probability for direct band gap semiconductors is much higher than that for indirect band gap semiconductors. Direct band gap semiconductors give up the energy released during this transition in the form of light, which is used for optoelectronic applications, for example, LEDs and lasers. Recombination in indirect band gap semiconductors occur through some defect states within the band gap, and the energy is released in the form of heat, which is given to the lattice. Another slight explanation in this topic. Basically, we use direct semiconductors for LEDs, and indirect semiconductors basically won't function as LEDs or other optoelectronic devices. So opto means light and electronic devices. Why? Because in order to transition from the conduction band to the valence band, it has to go through some defect states. So here one of the states is shown. So suppose this is a defect state. An electron going from the conduction to valence band has to first travel through this state. However, in a direct semiconductor, it can simply jump from the conduction to the valence band, giving the entirety of this Eg out at once as radiation, which we can calculate its wavelength using this formula. This wavelength is what we receive as light. However, here, since it has to go through these states, this energy is not sufficient, and as a result, what we end up getting instead is heat in the lattice. Now we come to variation of energy bands with alloy composition. The band structures of 3 to 5 ternary and quaternary compounds change as their composition is varied. There are 3 valleys in the conduction band at K is equal to 0, L and X. In gallium GaAs, the tau valley has the maximum energy direct with Eg is equal to 1.43 with very few electrons residing in L and X valleys except for high field excitation. In ALAS, the X valley has the minimum energy indirect with Eg is equal to 2.16 electron volt. Let's try and understand what is happening. So the first thing is that the band structures of 3 to 5 ternary and quaternary compounds change as their composition is varied. So basically, the band structures, which are these structures which we had discussed, they will change when the internal composition of these compounds are varied. Right? Now, what exactly is the tau valley and why are there these 3 valleys? You need not know. What you need to know though is that there are 3 valleys. One is tau, which occurs at 0 momentum change, and L and X. Now in gallium AS, so gallium arsenide, the tau valley has the minimum energy direct with Eg is equal to 1.43. So look at the tau valley, which occurs at K is equal to 0, as we have already discussed. You can see that the Eg is the lowest, so 1.43. This is also shifted, and in L is also shifted, X is also shifted upwards. However, this can change. Suppose in ALAS, the X value has minimum energy gap. You can see that the X value, which occurs at a higher momentum, actually has a lower band gap. So, this is how the energy band diagrams change with respect to composition of alloys when we use them as semiconductors. The important and key takeaway so far, what we have learned, let's go through a quick recapitulation. So we have learned that there were various energy band levels which recombine and they form energy bands once atoms form lattice structures. And then we learned that these bands may or may not contain electrons depending on what situation they are in. So the temperature, the light excitation, and various other factors. Then we learned that electrons can jump from this conduction and valence band from on being applied a particular potential difference. And we also learned is that when electrons jump, they either absorb energy if they're moving to the conduction band, or they give out energy if they're moving to the valence band. This energy, we learned, can either be light or maybe heat, depending on whether they are direct or indirect semiconductors. We also learned that if we use alloys as semiconductors, then their composition affect the energy band diagrams which we have discussed. And we see that there are three types of values which we obtain, which we learned as tau, L, and X. And depending on the type of semiconductor, we actually get a lower band gap by varying the composition. So tau value can have the lowest band gap, and X value can have the lowest band gap, or L value depending on what exact alloy we are using. Now we go to charge carriers in semiconductors. So in a metal, the atoms are embedded in a sea of electrons. We have all learned this from basic class 11-12 chemistry, and those electrons basically move under the influence of an electron field and produce a moving current. Now in semiconductors at 0 Kelvin, all the states are full in valence band and are empty in conduction band. So it does not conduct electricity whatsoever. However, at T greater than 0 Kelvin, the electrons get thermally excited to the conduction band, and what happens is the current starts to flow when an applied electric field is present. However, what is not immediately obvious but also exists is the fact that the empty states in the valence band may and often does also contribute in the flow of current. Also, introduction of impurities has an important effect on the availability of charge carriers. That's how we built diodes, and considering flexibility in controlling the electric properties of semiconductors. Basically, we have various types of semiconductor devices if you consider. So MOSFET and BJTs and PN junction diodes, all of these different types of semiconductors, they are made from these basic semiconductors, the material. These are used to make the semiconductor devices, and as a result we need considerable flexibility by adding impurities or changing the structure, composition we have already seen, and various other factors which we will very soon see. Let's introduce the concept of electrons and holes. What are holes? They are basically the absence of electrons in the valence band. As simple as that. So the empty states which exist in the valence band, once the electron has jumped to the conduction band, is known as holes. And we are aware that this only happens at temperature greater than 0 Kelvin. Quick question over here. What will happen if temperature is lesser than 0 Kelvin? Google it and let me know the answer. So the conduction band electron and valence band hole are created by thermal excitation of valence band electron to the conduction band. Then they are called as electron-hole pair. So if thermal excitation creates a hole, once the electron has jumped to the conduction band, then these two together are called electron-hole pair. Now after excitation, the electron is surrounded by a large number of empty states. So let's say in silicon at 300 Kelvin, the equivalent number of electron-hole pairs is 10 to the power 10 per centimeter cube. In silicon atom, it is 10 to the power 22 per centimeter cube, right? So, slight mistake, It is not in silicon atom. The silicon atom density is 10 to the power 22 per centimeter cube, and there the electron hole pair ratio itself is 10 to the power 10 per centimeter cube. So you can understand how dense the equilibrium number of EHPs is. Thus, the electrons in the conduction band are free to move via the many available empty states. The corresponding problem of charge transport in valence band is slightly more complex. So current transport in the valence band can be accounted for by keeping track of the holes themselves. Now basically this once again needs some understanding. Sorry. So we have learned that holes are the absence of electrons in the valence atom. However, what can happen is we have learned of the fact called recombination, that electrons from the conduction band go and occupy the valence band. Now think of it this way, that electron from, let's say, atom 1 goes and recombines with a hole of atom number 2. Now atom 1 has a hole while atom 2 no longer has a hole. Thus what we can sense is that the hole as if is propagating through the lattice. Actually the electrons are the ones which are moving and recombining with the valence bands, since they are free to move about in the lattice. However, this moving and recombination process also leads to an apparent shift in the position of holes, which also constitutes a current, because once again the hole is absence of an electron, so it has to have some charge. So for every electron moving with a given velocity, there is an equal and opposite electron motion somewhere else in the band. Now under an applied electric field, the net current is 0. Since for every electron j moving with a velocity vj, there is a corresponding electron j prime moving with a velocity minus vj. In a unit volume, the current density j can simply be given by 0, where n is the number of electrons per centimeter cube in the band and q is the electronic charge. So under an applied electric field, we basically get the net current in a semiconductor to be 0. This might be slightly confusing at first, but if you think about it, it actually makes sense. See, what happens is, whenever an electron is moving in a particular direction, there is another electron which is moving with the same velocity in the opposite direction. And this results in the net current density to be 0. Now if the jth electron is removed and a hole is created in the valence band, then the net current density, basically the Q, is minus Q. So what we get is a plus QVI, which is a current. So if you see that, if the jth electron is removed and a hole is created in the valence band, then the net current density, we get some current density. See, this first term, which is the net current due to electron, is 0. We have already discussed why it's 0. However, if we consider a single hole, then we do get some current density. Now thus, the current contribution of an empty state hole obtained by removing the jth electron is equivalent to that of a positively charged particle with velocity vj. Note that actually this transport is accounted for by the motion of uncompensated electron j prime having a charge of q and moving with velocity vj. Its current contribution minus q minus vj is equivalent to that of a positively charged particle with velocity plus vj. For simplicity, therefore, the empty states in the valence band are called holes, and they are assigned positive charge and positive mass. The electron energy increases as one moves up the conduction band, and electrons gravitate downwards towards the bottom of the conduction band. On the other hand, hole energy increases as one moves down the valence band, since holes have positive charges and holes gravitate upwards towards the top of the valence band. So let's quickly go through this entire section of constitution of current in a semiconductor, because this is a lot to discuss at once. So let's break it down into short, brief points. The first thing is that we learned about two things. First is electrons, and the second thing is holes. Now initially we discussed that hole is simply the absence of an electron in the valence band. So we are not treating hole as a particle, but we are treating hole as the absence of an electron in the valence band. However, we see that there are a lot of electron hole pairs in a single lattice structure, which can constitute current. Now, how do they constitute current? So, initially, if we just consider the electrons, then under an applied electric field, the net current is zero, since for every electron moving with the velocity Vj, there will be a corresponding electron which is moving in the opposite direction with the same velocity. However, okay, there's a problem in the slide. I'm so sorry. This should be under no applied electric field. So under an applied electric field, of course, there will be conduction. So under no applied electron field. I forgot to mention this. Just noted that there is no electric field. So under an electric field, we do get a current. So there should be no electric field. So that if we constitute, there is no current flowing. We know this because without an electric field, current cannot flow. So for every electron which is moving in, let's say, the forward direction, there has to be an electron which is moving in the backward direction, compensating the net current to be zero. Now, a very basic question is, why do the electrons need to move at all? Can't they just be still? The simple answer is, due to the thermal and optical excitation, these electrons often gain simply more energy than it takes to go from the valence to conduction band. As a result, they gain some momentum, and also if they are indirect semiconductors, then they will be forced to gain some momentum, as we have seen. As a result, they have to start moving in the lattice. Now, we saw that thus under no applied electric field, we see that the net current density is zero. Now, if we consider a single hole, let's say we simply take out a single electron from the lattice and we look at the empty state in the valence band. Like I had discussed earlier, this empty state is switching or basically moving from one atom to the other continuously. This movement will also constitute a current which will be equivalent to the negative of the charge of the electron, so minus q times Vj, which will result in plus q times Vj. So this is what we get the current for a hole. Now till this point we have assumed hole to be the absence of an electron. However, now that we have established that the current is q times Vj, we can treat hole as a single particle with the charge negative of that of an electron or plus q. So we start to treat hole as a particle. We also treat hole to have a positive mass. How exactly we will go into later, but remember this. So we have turned hole from simply a conceptual idea of the absence of an electron to a particle which has a mass and a charge. So basically a positive particle. And we see that it can constitute a current if it's moving through the lattice. However, at the same time, if there is no net applied electric field, the movement of this hole is basically compensated by the movement of another electron which is moving in the same direction as the hole, which results in no net current. I hope I'm able to explain this entire part. Okay, there's two more points which I discussed. So basically, the energy of an electron increases higher up in the conduction band. You can make sense of why that is very easily. However, what might not make immediate sense is that the energy of a hole increases downwards of the valence band. And basically, here we have to return to the initial analogy, that a hole is the absence of an electron. As a result, what happens is, see, the electron's highest energy level is the highest part of the conduction band, and the lowest energy level is the lowest part of the valence band. Similarly, if a hole is the absence or the opposite of an electron, has the opposite charge, so the opposite energy, we can simply take the negative sign and we can say that lower down the valence band, the hole will have a higher energy level. Since lower down the valence band, the electron has a lower energy level. This we are obtaining from the initial analogy that hole is simply the absence of an electron. As a result, what happens is the electrons tend to move towards the bottom part of the conduction band and the holes tend to gravitate towards the higher part of the valence band, since both naturally don't want to occupy the higher energy states. Now we come to the concept of effective mass, this is important in this chapter from the point of view of numericals. So basically, the wave particle motion of electrons in lattice is not the same as that of a free electron because of the interaction of the periodic potential of the lattice. To be still be able to treat these electrons or holes as free mass, we need to take consideration the rest mass, and we need to alter it according to the influence that the lattice has on it, right? Now, the calculation of this is very complex. We need not know how it goes on, but just a basic idea that it takes into account the shape of the energy band. So the curve, U-shaped curve we have obtained, the three-dimensional K-space, and taking appropriate averages on various energy bands, the effective mass is given by h by 2 pi whole square by the second order derivative of energy with respect to K. So you can easily remember this. This is basically reduced Planck's constant or h bar. So h bar square divided by the second order derivative of energy with respect to momentum. It's a very easy formula for effective mass, however it's rather important. This is a question which is given in the PDF. So find the dispersion relation for a free electron and thus observe the relation between its rest mass and effective mass. This is slightly important, however I'm simply glossing over and skipping it because this is a question and you would be better off learning this on your own. This table is rather unimportant. You just can take a look at the effective mass of holes and electrons. However, this is largely unimportant. Note that N stands for negative and P stands for positive. So N stands for electrons and P stands for holes. Now we come to the types of semiconductors. So there are intrinsic and extrinsic semiconductors. We will continue from types of semiconductors, intrinsic and extrinsic, from the next lecture. Thanks for watching this part. It has always been a pleasure. Almost been an entire hour since you were with me. We will continue with intrinsic and extrinsic materials in the next part.